Says it's time to go, so take it away, Amit.
Thank you. All right. Good morning, good evening, good afternoon, everybody, wherever you have joined from. Thanks for joining 6 query tuning techniques that will solve 75% of your performance problems. And I mean not yours, but your SQL servers. Now, the first important thing to note is that this is version 2 of this content. Version 1 was delivered, thankfully, with GroupBy last year in October. And I also put this up on SQL Maestro's YouTube channel, so you can watch it here. That's the link. So if you refer to the chat window, the link is available to you. I've been working with SQL for a couple of years now. My name is Amit Bansal. I am on Twitter here. The scripts are already uploaded on SQL Maestro's website, so you can log in and download the scripts that I am going to use here for part 2. And in fact, you can even download the scripts for part 1 as well. And there are a few more links here. We just did a SQL magazine, so the link is up there. And if you wish to connect with me, that's the URL. So that's quickly the introduction about me and some of my work. And all the links are there in the chat window. Now let's go and see what we have for the content. Now you will see precisely 12 scripts here, 12 query tuning techniques. And as I mentioned, from 1 to 6 was done as part 1, which you can watch in the YouTube video, the link of which I have given. Today, we are going to cover the next 6, which is version V2 from 7 to 12. So all in all, a lot of good query tuning content. And my hope here is that some of this content may be relevant to your SQL Server environment, and that's precisely the motivation. So of course, the background to this content, to this session is that whenever I get into a SQL Server performance tuning or a health check assignment, I come across these common patterns. And the intention here is to take these common patterns, create academic prototypes, and present it to the community. So of course, before I begin with the first demo, sincere thanks to the GroupBy organizers for choosing this session. Thanks, Ganakula, for moderating and hosting this session for me. And of course, everybody involved behind doing this great conference. I know what it takes to do an event, so thank you so much. So friends, let's get started with the first one. So you will see the number 7, 8, 9, 10, 11, 12, but note that this is like 6 techniques. So I'm going to start with 7, 8, 9, 10, 11, and 12. 7.1, expensive sorts. Now, the first thing that we talk about in sorting is all of you have worked with SQL Server for some time now as a developer or DBA, and you know that sorting is an expensive operation for SQL Server. The optimizer, the execution engine, needs extra memory grant because sorting happens in memory. And if there isn't enough memory, the in-memory data needs to be spilled down to 10 dB, and that's where the problem is. Now, more often than not, to be very straightforward with you when it comes to tuning the sorting thing, there are not too many remedies out there to sort. If you have to sort, you have to sort, which is if you want to really order by and give the presentation content on the application or in the report, and you have to present it in a specific order, you will have to put the order by clause. But there are a few caveats, a few things that you can do. And today I am presenting that stuff to you. So first, let's get started. Let me turn on the time on and IO on statistics so that we can see some execution metrics. I'm going to use AdventureWorks 2016. As I mentioned, I have created an academic prototype here for this one. Now, also turn on actual execution plan to look at the plan. Now, here is a very simple query. Look at this query. It says I need product ID, actual cost, and then I am using the row number ranking function because I want to give a row number to every record that is outputted. And I'm partitioning by product ID, which means my row number will reset by each partition of the product ID. And here is the interesting thing. We say order by actual cost. Why? Because my query says I want to rank the products based on cost, where the cost is greater than equal to 50K. And I'm ranking on cost, and that's the whole idea. I want to present the data when I'm partitioning, and I want to order by the most expensive or the most least one on the top and the most expensive at the end. And our filter is where actual cost is greater than equal to 50K. Let's run this and look into the execution plan. While this is running, we are also going to note how much time this takes. Now, when we talk about the execution time, there are two interesting aspects when we look into the time metrics. One is the elapsed time and the other one is the CPU time. Now, this is still running and it should complete in about 20 to 22 seconds. Let's see how this one is. Okay, so this completes. It takes about 21 seconds. And let's jump over to the execution plan. The moment you go and look into the execution plan, you will see that sort is expensive here. Let's zoom in a bit and see, yes, expensive, and cost is 45%. And you can also see that there is an exclamation mark warning on the sort operator. If I take the cursor over here, it tells me that, okay, there's some warning, operator used tempdb to spill the data during execution, blah, 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 which means that spilling was done to tempdb. This is the common thing that we see with sort. Now, how much time this has taken? This has taken about 21 seconds. So I'm going to write 21. Now I will keep this window as is. And before we try to fix this, we will see is ranking the problem. Now, right in my demo here, I've used the row number function. Now, when I presented this demo in some other session with the customer, there was a question that was raised, which is that, is ranking function really causing here, the slowness? And I wanted to prove that no, it's not really the ranking. This is actually happening because there is an extra effort by the CPU here to order the data. And of course, in-memory sort is happening. Transactions table is a huge table. It has a few million rows. And that's the reason why sorting is creating that slowness. So what we should do is just take a step back, write a very simple query where I am not using the ranking function at all, and I'm just simply ordering. And let me take into this new window here because I don't want to disturb that demo and include the actual execution plan here. And let's just go ahead and run it. Why am I doing this here is just to show you that it's not because of the ranking function. If you have a simple select statement also with the order by clause, it might take more or less the same amount of time. And that's what we are going to see. So let's wait for a few more seconds. And remember, this is digressing a bit. So this comes to about 20 seconds or so. So you see the difference is not much. Let's jump over to the execution plan, and you still have sort as an expensive operator here with 45% cost. And there is an exclamation mark warning. So spilling is also happening here. I digressed from the demo a bit just to show you that, just a second. I digressed a bit just to show you that this is not being caused by the ranking function. So let's close this for the moment. All right, so let's come back here. So yes, this took about 21 seconds. So we say no, sort is the problem. It's not about ranking function. So what is your first fix? The first fix is do not sort at all. And I put a smiley out there, of course, because all of you are thinking, well, that's not the solution. But let me take a step back and tell you that could be the solution. Here is the background. With many customers, when we see that sorting is causing that slowness and it's making the execution time go way above expectation, and I dive deep into the query and the requirement, the reporting requirement or the application requirement for that query, I have seen developers putting order by clause just for the sake of it. Just for the sake of it, simply because there is a habit, there is a tendency, a pattern of putting order by clause. We human beings want to see data presented in a specific order. Order by customer ID, order by name, order by city, order by date. That becomes a natural human tendency. And I see that even though the reporting or application requirement does not specifically ask for it, yet we put the order by clause. Now, for all of you, I'm assuming you're all technically very well versed, so that is not the solution for you. But yet I wanted to call it out that do not ignore the very basics. Do not ignore the very basics. See to it that you do not have order by clause if it's really not required. And let's turn this put this into a new window and look into how much time it takes without the order by clause. So I'm going to turn this time on and IO on here, execute, and turn on actual execution plan, and now run this simple query even without the ranking function, and remove the order by clause. Let's see how much time this takes. So if I execute this, the demo at this point is looking very, very trivial, and I'm building up on something. If you have watched earlier sessions from me, you would see something very, very interesting coming up as we come to the closure of this demo. So what I've done is just removed by an order by clause there. Look at the total execution time. Now it is 18 seconds. So here is the story, friends. You might be wondering, what's the big deal? The first execution here took about, let's go back here. The first execution took about 21 seconds, right? The second execution here without the ranking function took about 19 seconds, and this one is taking about 18 seconds. That's not very convincing. So what's going on? Now let's go and dive deeper into this stuff. So you saw that I have turned on set statistics time. So if I go to the messages, let's see how much time did the query spend on CPU. So the one with order by, this one, right? Order by in our ranking function, the elapsed time is about 21 seconds that you can see, and the CPU time is about 15 seconds. So 15499 milliseconds. So about 15 seconds were spent on CPU. If I jump over to this one without the order by clause and jump over to the messages tab, let's scroll down here and look at the total time. So elapsed time is about 18 seconds. That's fine. That's not very convincing. But look at the time spent on CPU. It is just about 6.4 seconds. At max, 7 seconds. So the point here is that 15 seconds of CPU time comes down to 6 seconds. Now is this is very, very interesting, because when we do query tuning, we are mostly looking at elapsed time, the total time the query has taken to finish its execution. When you look at elapsed time, it is from the point you fire the execution until the last byte of the data is served on the client. And in our query tuning efforts, when we are only focused on elapsed time, and when I take this specific example as a very typical example, I would be like, wow, even if I have removed the order by clause, the elapsed time is more or less same. It's like 21 seconds, 20 seconds, or 18 or 19. But remember, SQL Server is serving all the data in Management Studio here. Can you look at the number of rows there? I think it's about 3.9 million or something. That is the amount of data that is being served in the results pane, and that's taking quite a bit of time. That is the reason why we got to focus on the CPU time. So removing the order by clause actually saves a lot of CPU time. If I jump over to this one and go to the results pane here, it's the same amount of data that I'm getting here. So in both cases, huge amount of data is being served on the client, and that effort, that thing is getting added to the elapsed time. My focus on query tuning here is the amount of time the query is now spending on CPU, and I have 100% gain there, which is 15 seconds versus 6 seconds. That is the point to note. But all of you who are watching this demo, you definitely want that elapsed time should also be reduced, isn't it? Well, I will, as a concluding part, I will show you how even the elapsed time comes down. But let's carry on with the demo. Now, remember this demo, there's so many learnings in this demo, right? Just not the order by clause, but in your typical query tuning efforts, I will repeat this again, friends. Do not only focus on elapsed time, please also focus on CPU time, right? Your thread, the thread that is executing, or the threads, if it is a parallel query, how much time are they spending on CPU? Now let's move forward. So ranking was not the problem. Solution one, fix. Okay, fix one is don't sort. Now, not very convincing. You want to sort. Let's look at this technique now. I have the same ranking function, and I learned about ranking functions when they were introduced in SQL Server 2005, but there were so many things to learn about this ranking function, the over clause. And in one of the demos today, I'm actually going to talk about the over clause and partition by, which is like within the ranks if I want to group by a certain attribute like product ID in this example, and then order by. Now, the interesting part here is in the previous one, you're actually ordering by actual cost. As I said, ordering may not be required because you're just ranking. So I have already given partition by product ID. I can say order by select null. Now that's the trick to avoid sorting with the ranking. And this execution will also have less CPU time. And that is our win here. So if I put this up here and execute this, you will again see that elapsed time will probably be around 20 seconds, but the overall time the thread will spend on CPU will be considerably much lesser. And I put these comments here, which is focus on the amount of time the query is spending on CPU. So looks like this would be done in a few seconds. Yes, it takes about 20 seconds. Let's jump over to the execution plan. Of course, there is no sort because you didn't ask for sort. And then if you go over to the messages tab, you can see CPU time about 7 seconds. And that's your gain there. Now, what are our other solutions, right? Fix 2 could be, now, why I took ranking as an example, because this is what I had been seeing with customers who are actually using ranking functions like, let's say, row number or rank, dense rank, entile, and all of them are ordering by the attribute where it may not really be required. The other is to pre-sort the data by creating an index. This seems to be a more common approach where if you pre-sort the data using an index and put the relevant attributes in the index that your query wants, that may also serve some magic. But of course, before you just go ahead and create a non-clustered index or probably a covering index for a specific query, be very mindful of looking into existing indexes that could be modified, the amount of data this non-clustered index will actually store, and there could be a bit of maintenance overhead also. So of course, all the caveats and all the learnings and all the experience with non-clustered indexes will come into play here. But then you need certain techniques and solutions. So here is one. What I am doing here is I'm creating a non-clustered index where the data is now being sorted by product ID and actual cost. And I purposely choose these two columns as part of the covering index because my query actually uses them. And then if you take this query, index is being created now, and let's copy this now here. And now I'm going to run this one. And now when I say order by actual cost, my index is going to be used. So what's the name of the index? Let's go and see. This is IDX actual cost, right? So let's go and run this and see how much time this takes. Okay, so while this is running, let's go back and see. Okay, we are up in the cleanup section. So this is your fix 2, which is pre-sort the data with the help of an index. Now the overall execution here will again take about 20. Okay, there you go. We complete it, and it takes about 20 seconds for the query, and we jump over to the execution plan. We are scanning the index that we created, and where is the object there? There you go. So this is the object we created. So SQL Server Optimizer is using the index that we just created, which is what we want. It's scanning. That's fine. There's no sort here because the data is pre-sorted, and that's the fun part of it. No sorting here, even though we have the order by clause, right? Because the data is pre-sorted. Let's jump over to the messages tab and look into the amount of CPU time, and you can clearly see about 6.9 seconds. So again, about 7 seconds. So the learning here is don't only look at the elapsed time, focus on CPU time, and you have seen how CPU consumption reduces quite a bit when you try to get rid of either sort or in ranking functions use this technique, so to say, which is kind of lesser known, I would say. A few years back, even I had not known about this. And then, of course, is pre-sort the data using the index. Sorting is a huge topic. Not only this, we run into a lot of problems related to short sorting or hash aggregates, etc., where they ask for extra memory and there are memory grants that are pending. We troubleshoot all of that, so on and so forth. Now, the next part of this one, or rather I would say the concluding part, is what if, okay, let me drop this index because as part of the cleanup, okay, drop is done. Now, friends, the total elapsed time. Now, as I said earlier, about millions of rows are being served on the client, right? And that's taking time. That's getting added to your elapsed time. So what is the optimizer really doing? Optimizer is fetching the data from disk or from memory. And while it's fetching those 8K pages, the buffered pages, it's serving on the client. What I did, just for the purpose of this demo, to kind of show you some real stuff with this, I have put the scripts in 7 expensive sorts here. So, I mean, those of you, if you're downloading the scripts, follow this. I will go into 7 expensive sorts folder, and I have created 2 scripts here. One says with order by, and the other one says without order by. Let's go and open this one and see what does this have. So this has the query with order by clause. Let's close this. And the second one has the query without order by. Same query, and there is no order by there. I mean, select null. Now, what we will do is I have created 2 command files here. First one will run the order by script, and the second command file will run without order by script. And what are we doing in both the cases? We are using ostress utility as part of RML utils, and I am calling with order by SQL. That's the file, and I am creating 8 threads because I have 8 cores, so just kind of aligning it, and 1 repetition. This is what I am doing now. And of course, the second one does the same, just that it calls without order by. Okay, these are the 2 ones. Okay, so while we did this, why not show this to you? And this one does the same, just that it calls the other file. Now, why am I doing this? I am doing this to prove to you that that 20-second stuff with a single thread actually happened because millions of rows were served on Management Studio. Now in the command file, the output is not going to come because of ostress exe. So let's go and fire the first one. Okay. 8 threads are being created. Beginning execution, you can see 8 threads are processing our queries, only 1 iteration. Let's look at the overall execution time here. This is with the order by clause. Sorting is happening now in memory. Let's look at the overall execution time. Should be about, okay, 21 seconds. Now just compare this. These were 8 threads running, right? We have 8 cores here, and overall execution was 21 seconds. Take a note of it. And you can see nothing was being served on the client, so ran pretty fast, 21 seconds. Now comes the fun part. The second one, without the order by clause, exactly the same stuff. 8 threads are running, and hopefully this should complete much faster because we use that trick. You know, I would call that more as a trick with the ranking function, where you say order by select null and you don't put any attribute in the order by clause. Completes in about 16 seconds. So you can see the gain there. This is because of less time being spent on the CPU. Okay, friends, I am sure there will be questions, but as told, requested to all of you, we can have the questions at the end of the session. Wow, the first demo itself took quite a bit of time. Let's relax a bit with the second demo. Now we are moving on to the second demo, file number 8, cardinality fix. Now, in this demo, when I'm presenting this to you, I know many SQL experts in the community will be furious because I'm trying to show you a hint. And when we talk about query hints, you know, it's always said that query hints should be used very seldom and should be the last resort in your query tuning efforts. I'll tell you, we have been using query hints quite a bit, and it has worked well. The idea as to why Microsoft or community would recommend that query hints should be used less is because you got to use them with care. In many scenarios, what happens is when you embed query hints into the queries, you don't reenter them. They are left there for months and years, and temporarily it will fix the problem, but later on, if you're not monitoring those workloads well, they may cause other issues, and that's where the problem comes from. But nonetheless, it's a query tuning technique, and why not look into it? So let's get started with this. Okay, so I'm going to turn on set statistics time as well here, include actual execution plan, and use AdventureWorks 2016. Now here is a very simple query. It says select start from sales order header where salesperson ID is equal to @SPID. Now what happens is @SPID, I mean, this is salesperson ID. This is not SQL Server SPID. So sorry for this variable naming here. This is not session ID. This is salesperson ID. We have used a local variable. Now the optimizer, when it has to execute this piece of query, it does not have the value for the variable until runtime, and that causes a bit of an issue. So only during runtime will it have the value of the variable, but by that time the plan is already created with a default estimation. I will not get into the internals of the cardinality estimation formula here, but that also is available. Let's go and execute this and see what's going on. So when you execute this and jump over to the execution plan, you can see that a scan operator has worked behind the scene. If we go and look into the results, you can see 16 rows. So friends, this table, sales order ID, whatever, has about 30,000 rows or something, 30K. You have got only 16 rows as output. And this means the query is highly selective. Yet SQL Server has employed a scan. If I take the cursor over this arrow between filter and select operator, you can see that the cardinality estimator estimated that 1700 rows could probably be returned. That is the estimation. But actually we get only 16 rows. Now, let's not get into the debate of why cardinality estimation went this way. There are all sorts of logic and formula, and this is the new version of cardinality estimator in SQL Server 2019 that I'm running on. A few years back we had the old cardinality estimator, so a lot of that stuff is there. But that discussion and debate aside, this is the current state of scenario here, that with default estimation, the optimizer is estimating 1700 rows, and I'm only getting 16 rows. So there's quite a bit of difference in this estimation. And SQL Server decides to choose a scan there. Now what can I do? For sometimes, to fix performance of such queries, I would employ an optimize for hint. And I already warned you here, use these hints with care. They may temporarily fix the problem, but you need to keep monitoring. And the whole idea is using any tuning technique that is available at your disposal. You got to use them with a lot of responsibility. When we recommend customers doing something like this, we are recommending this with full authority and responsibility that, okay, you got to use this. This will fix it temporarily, but we got to continue monitoring, find some other solutions, etc., etc. Those discussions are aside. What I'm trying to do here now is, when we use SPID 285, right, that remains static. But I'm telling the optimizer that instead of optimizer deciding the default value to be substituted or to be used for this local variable, I am telling optimizer that, please, why don't you optimize this query for value 285? Now I can put any other value here, that's fine. But right now, just to show you as part of the demo, I'm putting the same value that is there in my select, which is 285. Let's first run this and see what's happening now. So if I run this, turn on actual execution plan and go and execute this, you again get the 16 rows. This is what you expected. The query is highly selective. If you jump over to the execution plan, now you get a seek. You're not getting a scan plan. And this is the trick here, that for the query being so selective, highly selective, seek was a better option. But because the optimizer did not have any value to sniff, right? Now optimizer has some value to sniff, which is 285, and it is preparing an execution plan for that parameter value 285, and it gives you a better plan. That's the whole idea. Now it's a no-brainer that if I take both of them and compare, and I'm sure you can expect what you expect, which is look at the cost, 92% versus 88%, and that's the difference between scan and seek here. So the other point here is, why am I putting 285? Your question could be, well, salesperson ID could be anything. It could be 1, it could be 100, it could be 150, it could be 285, it could be 375, it could be any value, right, from the client application for the reporting. Why do we freeze on 285? Well, here comes the so-called responsibility, authority, research, and diving deep into the querying pattern. We got to track this query and observe the variety of parameters that are coming in. Now, my research said here that the variety of parameters that are coming in are actually making the query highly selective. I'm almost always returning about a few rows less than triple digit. So it could be 5 rows, 50 rows, 20 rows, 30 rows, so on and so forth. So pick up any value that promotes a seek plan, because most of the queries parameters are highly selective in nature. That is the key point here. So if I actually put a value here, which will give me, let's say, a few thousand rows, let's say there's a salesperson ID who's a star performer and has done hundreds of sales. If I put that salesperson ID here, it may resort back to the scan plan and it would defeat the purpose. So the idea here is to use a salesperson ID that will inject a seek plan into the plan cache. So this was fixing the cardinality estimation using optimize for hint. All right, hope you're enjoying the demo. So that was sorts and cardinality fix. Let's move to the next one, T Sql rewrite. Now these rewriting T Sql I have seen is one of the most difficult things to do. It is easier said than done. In most cases, I see that DBAs or developers, when they're troubleshooting query performance, and when they are being asked to rewrite someone else's code, I'm sure all of you have come across this at some point in time, where you are asked to rewrite someone else's code, and the kind of expression and behavior you would have then. So I know it's very difficult, easier said than done, but nonetheless, let's give you certain templates and certain ideas behind this. And I'm using an age-old database here. If you could remember pubs and Northwind, which we used to use in SQL Server 2000, these were in fact the first set of databases. I started learning SQL with pubs and Northwind, so I still have them here in every VM that I work with. So just love these databases. Okay, so what are we doing here? In this one, we are looking at rewriting the queries, and I have two examples to it. So this third one and the fourth one as a follow-up. So let's start with the third one here, the first one, subqueries versus cross join. What are we trying to do in this query? We are going to calculate two aggregates for each sales row. So there's a table here. Those of you who know pubs, even if you don't know, it's all fine. dbo.sales, a simple sales table where one record represents each sale item, each order, and it has the quantity, it has the amount, and all that stuff, right? So for each sales row, we are going to calculate two aggregates. The requirement is, first one, the percentage row contributed to the total sales quantity. And the second is difference between that row's sales quantity with the average quantity overall sales. So what we want to do is, first we want to calculate the percentage. A specific sale item is what percentage of the overall sales. And then we want to compute the average of all the sales and see the difference between that specific sale item with the overall average. Now, when you run this query, let's first run this and get the output. Okay, here is the output. Okay, let me turn on actual execution plan. Okay, there you go. So what do you get? You get the quantity for each sales there. This is the percentage contribution, and this is the difference with the average. That's pretty much the logic here. When you look at this query here, you will see that we have employed two subqueries here. One which is calculating sum and the other one which is calculating the average. If we jump over to the execution plan, and now let me involve, let's do a bit of interaction. Why don't you use the chat window and please tell me, where do you see a problem? The execution plan is right in front of you. Let me pause the share and I will monitor the chat window for a few seconds. Look at the execution plan carefully. Where do you think we have a problem? Not sure if the chat window is turned on for the participants. Okay. We're getting a few responses. Some of you are bang on, and that's great. So you're saying that we are touching the sales table 3 times. So David says, okay, we hit the sales table twice, but if you see, David, we are hitting the sales table 3 times. Is that what all of you are seeing? That's where the problem is. So if you look at this portion, okay, let me resume the share. Hope you can see the screen again, and look at this one, and this one. So we're hitting the sales table 3 times. So the question is, why are we hitting the sales table 3 times? Well, quite easy to identify. Of course, one for the outer query and one for each of the subquery. And there is a tuning opportunity here, thinking in terms of cross join. Now, my experience working with DBAs and developers is that using subqueries comes as the first option. I don't know, maybe because writing subqueries tends to be an easier approach, you know, from a developer perspective, writing T Sql. But all of you may have your own experience. So when we are presented with the T Sql problem, it's like a mathematical sum, isn't it? It can be solved in many different ways. And one of the first things that's come to our mind is to use subqueries, but the same query can be rewritten as a cross join. So if you see here, we have the outer query here, and I have put this query as a single subquery, and I'm doing a cross join here. So if I execute this portion, it's giving me the sum and the average quantity. Let me just bring it down a bit, and you will see that this output is being cross joined. So I'm using the syntax here, which is DBO sales, comma. I could say cross join, but I just did comma with this output AGG. So this result set is cross joined with the outer query. So if you run this one now, execute this, jump over to the execution plan, you will see that you have cut down on the scan to just twice, one for the cross join query and one for the base query. And of course, this will have some performance impact, and not to get into the execution metrics because the query is relatively working against very small set of data. So the impact will not be well known, but you can always look into the execution plan metrics, and the optimizer clearly tells you the cost here is 60% versus 40%. Okay. Now, this was a very simple thing that we did with rewriting, but let's go one step further and open up the fourth example now, which is using the over clause. And I'll tell you, I was completely taken by surprise one fine day, which was years back, when I learned that over clause is a great performance tuning technique independently. You know why I use the word independently, and let me admit and confess to all of you, first time when I was learning about ranking functions will use the over by clause, right, which is part of the syntax. Over clause means the window of the data that you're working with, and for some reason I assumed that over clause can only be used with ranking functions, and that's where I went wrong. over clause can be used independently. I know many of you may be laughing right now, but then those moments come in everyone's career, right? So I learned it in a real funny way, which is what I'm trying to show you now is this problem of calculating multiple aggregates, right? So what we were doing in the subquery and even in cross join, we were calculating the aggregates, sum, average, and here in the cross join also we were doing sum and average. Now I am going to rewrite this using over clause. And over clause solution is quite interesting. There's no ranking function here. We simply say over, and of course I have to take care of the formatting as well here, just to make sure that the query does not throw up any mathematical errors. But when we are calculating sum over and average over, and our window of data is sales here, over clause is going to scan the data only once. Unlike the subquery, it will have a single pass over the data, which means in a single pass, I can actually compute multiple aggregates. And that's the key thing here. So if I run this, you will get the output. And let's turn on actual execution plan, do this again. You'll get a different execution plan here because of the over clause implementation. And now let's do a performance comparison. So we're going to take this one, the cross join solution that we did, and the subquery. Let's compare all three. Now this is what we all do all the time, right? We rewrite and we look at performance improvements. So let's jump over to the execution plan, and I'm not zooming in right now here, but you can see 49%, which is your subquery, 33% cost, which is your cross join, and last one, 19% cost, which is your over clause. And over clause is really great. If you look at, let's look at this one. Okay, see here, look at the difference here. Of course this is just a prototype, you would probably not do anything like this, but just trying to show you calculating multiple aggregates using subquery, sum, count, average, min, max. If you run anything like that, of course you're talking about a single you're talking about multiple passes on the sales data. Look at this, right? 6 times you're scanning the data here. And of course, if you're using the over clause, the same query, right? Let's run this and jump over to the execution plan. 84% cost. Let's look at the plan. Simple, almost the same, because in a single pass, you are computing multiple aggregates, 16% cost. So go back and look at all your queries that are computing multiple aggregates. It is really advantageous if you're using computing multiple aggregates. Over clause may be highly beneficial. All right, friends, so we come and end to the fourth demo. So we did expensive sorts, cardinality fix, T Sql rewrite, and over clause. I hope all of you are enjoying the demo. Let's jump over to the last two. I think we are doing pretty good with time. TempDB. Let's jump over to TempDB. Now, this is not really, technically speaking, not really a query tuning technique, so to say, but any technique that you apply with SQL Server that improves your query performance could be termed as query tuning. And I thought I should take this up as an example, faster inserts in TempDB. Again, the motivation behind this is, I'm assuming many of you would know that when we have this TempDB database, right, which is a throwaway database, and where any insertion that you do in TempDB, whenever you are creating temporary objects, SQL Server would only have minimal logging for TempDB, right? It will record enough information to perform an undo, but a redo is not required, simply because when SQL Server has to do a crash recovery, the data that is there in TempDB would anyway be discarded. So there's no redo required in TempDB. This is kind of not very well known. I kind of realized it in last few months. So I thought, let's prepare a quick demo to show you how this entire thing works. I'm going to use AdventureWorks 2016 again, and we have a very simple table here. What is this table? Okay, T1, and I'm creating one column, which is of type integer, straightforward. And then I'm using a loop here to insert the data into this table. Now remember, this table is created in AdventureWorks, which is your user database. We are inserting about 100K rows. Let's fire the loop. Now this is running. We will take this query, count star from T1, and put this up here. Let's see. Okay, so just for you, okay, the query is still running. This has been about 16 seconds now. Let's see what's going on here. We are trying to insert 100K records. We have only achieved 27 now, and every time I'm refreshing, we see a jump of about 2K. So this is taking quite a bit. You're inserting 100K records. So we have crossed over half a minute now. We are in 35 seconds now. And 45K now. Okay, so about we will need a few more seconds. So why spend that much time? Let's stop the query. We stop the query at about 49 seconds, about 50 seconds, and we just have about slightly more than 50K records being inserted. This is happening in your user database. It's taking quite a while. Now, let's try to do the same stuff in TempDB. I'm going to use TempDB now. And let's create this table in TempDB, exactly the same table, T1. And now you know the object is being created in TempDB. Okay, and let's go and insert the rows now and watch for a moment how much time this takes. All right, so I'm clicking on execute, pay attention. You do that and boom, you're done. This has taken just about a second. Look at the clock there. Time 1 second, something that was not even completed in close to a minute, this completes in a second. Should we check the data? Let's verify the data. And yes, you have about 100K records. Now, why is this happening? This is happening because TempDB in SQL Server, for TempDB, you have minimal logging. Now, remember, this minimal logging is quite effective. As I said earlier, the explanation behind this is whenever you are working with temporary data, do not create it in user databases. We see this practice of, I see this practice in stored procedures, or we create tables, staging tables, for example, in user database, and those tables are then deleted diligently at the end of the script. That's fine, but try to do that in TempDB, or just create temporary table like hash T1 or something like that, which means now TempDB will have minimal logging. So the redo portion is not going to be recorded, and that's going to save a lot of time. Remember, friends, this demo is not about eager writes. I kind of say this in advance because in another session somewhere someone commented that, is this eager writes? No, this is not eager writes. This is not a bulk operation, right? I'm simply doing an insert into. This is not a bulk operation. And eager writes is enabled by default in latest versions of SQL Server. So do not confuse between the two. This is about minimal logging and how certain crude operations can go better. I have also blogged about this. While I'm answering questions at the end of the session, I will pick up the blog URL and I will share it with all of you so that you can read more about this stuff. Okay, friends, so let's close this TempDB and move on to the last demo, index tuning. I mean, why did I pick up an index tuning example in query tuning? There are two reasons for this. Reason number one is, of course, when in last GroupBy, I did this first part of this session, which is 6 query tuning techniques, version 1. I did not cover anything about indexes. Look at the folder here, right? We talked about I mean, from an index tuning perspective, I talked everything about query, non-sargability, seek not happening, implicit conversion, dynamic SQL plan cache, bookmark lookups, and parameter sniffing. So folks were like, okay, there's nothing related to indexes. So I thought, why not include indexes in today's demo? The second thing is, technically speaking, this is not a query tuning. I mean, strictly, this is not query tuning. I am actually tuning the index. And when you tune the index, of course, its impact can be seen on query execution and query performance. Indexes are searching mechanism, right? And if you're able to search faster with the right index, of course, query performance will improve. So irrespective, technicals apart, I hope you will like the demo. So let's start with, again, AdventureWorks 2016. And we have a table here called person.person. Let me just select this data and show what this table is like. Okay, so it has business entity ID, it has first name, last name, it has a column called email promotion also, which has just three values 0, 1, and 2, as you can see in the sample data out there. Now, what I will do is first I will make a copy of this table. Let's create another heap and call this as contact2. And I'm coming to the problem statement in a while. Okay, so we have created a heap, and all of you know heap. So there's no clustered index, there's no non-clustered index at this very moment. Now I'm going to create a clustered index on business entity ID. Let's go and do that. So on contact2, which was a heap, now has a clustered index called business entity ID. So there are no more non-clustered indexes. So what do you see with HSP help index? That this specific table has only one clustered index. Clustered index can only be one, and we have the index key as business entity ID. Now is the problem statement in front of you. What I want to do is I want to design an index for this query. Look at this carefully. Okay, I don't want to confuse you, so I will remove max stop here just for the purpose of demo. This select statement retrieves business entity ID, first name, and email promotion. Only 3 columns from the base table, which is contact2. All of you know that there is already a clustered index on business entity ID. And my predicates, my filters are on first name like L% and email promotion equals to 1 and business entity ID less than 10,000. And again, I throw this problem at all of you, and let's take a minute or so. You design a non-clustered index for this query. I can of course show you the solution in a few minutes from now, but you design a non-clustered index for this query. Now let me help you. Let me help you here. When you are designing a non-clustered index here, feel free to make it a covering index, no problem. Feel free to do that because you have these 3 columns. You know that business entity ID already has the clustered index. So when you create a non-clustered index to improve the performance of this query or any non-clustered index for that matter, the clustering key value will always be included in the non-clustered index. So your non-clustered index definition may not have business entity ID, which means your non-clustered index will only have first name and email promotion. I hope all of you are in synchronization with me here that your non-clustered index can only have 2 columns as part of your index keys, first name and email promotion. You're free to use the include keyword here. You're free to do that. But before you decide on the index, take a note. First name like L%, look at the predicate. Email promotion equals to 1 and then business entity ID is less than 10,000. We are using different variety of relational different operators here, like operator, equality operator, and a relational operator. Keep that in mind, and also keep the selectivity pattern in mind. I'll call out the selectivity for all of you. Like L% will actually give me 800 rows. Okay, so it will give me 800 rows. Email promotion equals to 1 will give me approximately how much data. Let's just see how much we have in, I think it was 25%. So, okay, 19,000. So approximately 20,000 rows we have. And just to be fair to all of you, this is going to give me about 5,000 rows. Okay, and this one will give me less than 10,000. And you know that there are about 19,000 rows there, 19,972, about 20K. So this is going to give me about 10,000 rows. That's the selectivity pattern for each of the predicates. First name like L% will give me 800. If I just use that predicate, email promotion equals to 1 will give me about 5,000 rows. And business entity ID, you know, it's from 1 all the way to 19,972. It's going to give me approximately 10,000 rows. With this in mind, design a non-clustered index. And can you just put the pseudocode in the chat window? Maybe you can just choose the columns in the order you want, or if you want the include keyword, Let's make it some fun. I'm looking at the chat window to see what answers are coming up. Let me pause the share. Okay. Okay, great. We are getting some responses. So first solution, we are creating an index on first name. Okay, that's an index on first name, no email promotion. Second answer that is coming is create an index on first name, include first name. Well, that wouldn't make sense because you already have first name there. Okay, then we have another index option, which is email promotion, comma, first name, comma, business entity ID, right? So Vinay, as I said, Breck, well, I read out yours. I'm reading out Vinay's now. Email promotion, comma, first name, comma, business entity ID. So Vinay, business entity ID is not required because we already have a clustered index on business entity ID, right? Sasson has an answer there. Index on email promotion and include first name. Well, that's a good option. So we have an index being created on email promotion. So the index key is only on email promotion, including first name. Okay. We have another option coming from David, which is first name, comma, email promotion. This seems to be a good choice, creating an index on first name, comma, email promotion. And probably David has chosen this because I think David, and rightly so, you're probably focusing on the selectivity because first name is highly selective, and going by some indexing guidelines, you put the most selective column as the first column in the index. Some great responses. So David has, okay, then we have another one. Sudhakar says, let's go ahead and create an index on email promotion and first name. So here the columns are reversed, email promotion, comma, first name. Sudhakar, very good choice out there. And let's get into the details in a while. Milind has another question, response, index on first name and include email promotion. Okay, friends, all sorts of answers have come actually. I guess all of you have covered everything, all possibilities. That's good. Okay, now let's follow this technique of elimination, and I'm sure if you've not seen this demo before, you will probably love this. We are creating a non-clustered index to satisfy the performance of this query. Let's follow the round of elimination. I'm going to eliminate business entity ID. Why? Because there is a clustered index already, and every non-clustered index automatically includes the clustering key value. Why? Because it can perform bookmark lookups or just generally lookups based on these IDs. So business entity ID is eliminated, which leaves me with two columns, first name and email promotion. These are the only two columns now in my select list. So let's first eliminate the include keyword. So some of the responses have included either first name or email promotion. I would not use the include keyword for either one of them. Why? Because I want to perform a seek. The question you have to ask yourself, when we have an index, there are two access methods, plain speaking, right, in a straightforward way, high level overview. There are two access methods. We have the seek and we have the scan. When I look at this operator, this filter here, first name like L%, I can actually seek on first name with L% because we have a leading wildcard character here, the character L and then percentage. So this is seekable. If for some reason this was percentage L, then this was not seekable, right? This is an important thing to note. So I'm going to seek on first name. Likewise, email promotion equals to 1. Friends, we're using equality operator. So this is definitely seekable. So if both the predicates, first name and email promotion, are seekable, why would I put them in include keyword? I would not put them in include keyword. You put columns in include just for the purpose of covering attributes that on which you do not want to seek, and you just want them to be available in the leaf level of the B tree structure only for the purpose of retrieval, only for the purpose of covering. You will put those columns in included keyword. But in this particular scenario, I'm actually going to seek on both of them. So I'm going to put both of them in my index key definition. I repeat that. I'm going to use first name and email promotion, both of them in my index key definition, and I am not going to use them in include because I'm going to seek on them. This means I have only two choices, either first name comma email promotion, the order of columns, or it could be email promotion comma first name. So this leaves me with two choices, two popular choices that you could give, and these are the ones. Option 12 and option 13, contact composite 4 and contact composite 5. These are the two options I have, and the idea is very different. Both are covering indexes because business entity ID is already there. I'm not using included keyword here, not required, because I'm going to seek on both of them. Now the only difference is on contact composite 4 I put first name comma email promotion, and in contact composite 5 I put email promotion comma first name. And friends, before the climax, here is my last question to you. You give a choice, choose either 4 or 5. Use the chat window, put 4 or 5. What are you preferring? Are you preferring contact composite 4 or are you preferring contact composite 5? The only difference is the order of columns. Make a choice and then we will see what is the choice of the optimizer, right? Use the chat window. Let's see what choices are coming the most. Looks like the screen sharing was paused, but I will just kind of repeat this again. Okay, so we are coming to, this was the portion I was talking about. Create index option 12 and option 13, contact composite 4 and contact composite 5. Both the indexes look similar. The only difference is the order of columns. Your choice now. And let me just see what responses are coming in the chat window. Okay, we have a lot of people recommending 4. Why is someone recommending 12? Okay, 12. Okay, option 12, which is 4 again. Fine, fair enough. Okay, very few are going for 5. Okay, all of you should participate. This is your time to vote. So the ballot is open and I'm just waiting for a few more seconds. I've hit right on the clock, 1 hour over. Thank you, all of you, for participating. Okay, great. A lot of responses. Now there's more responses coming as 5. What is this pattern? First, they were all 4, 4, 4, and suddenly there's a response of all 5. Great. Okay, so let's do one thing. Let's go ahead and create both the, create both the indexes 4 and 5. Okay, done. Now let's go back and run the query and let's see what is the optimizer choosing. So I'm going to run this, turn on actual execution plan. Remember, contact composite 4 has first name comma email promotion. Just to show this to you once more, contact composite 4 has first name comma email promotion, and contact composite 5 has email promotion comma first name. Now we are asking, we have created both the indexes. We are asking the optimizer which one would it prefer. Jump over to the execution plan. You have a seek happening. This is a covering index, as you all know. And let's take the cursor over here. And friends, the winner is contact composite 5. That is the winner. It's not contact composite 4, first name comma email promotion. And I will tell you, many of you might be surprised with what the optimizer is doing here. So let's first get rid of a few myths. First myth, because we created contact composite 5, that was chosen as the by the optimizer because it was created second. Well, of course, I do this as a myth because this also comes as an answer. So there's nothing like that. The order of creating index really here doesn't matter, whichever order you create in. Okay, so that's the first myth buster. So that's the first one. Second myth buster here is order of columns. Does it matter? Order of columns. The second myth buster is optimizer could just choose any index because contact composite 5 and 4 both are the same. They have the same columns. The order is different, but they're essentially the same structure wise, so to say. So the optimizer can pick up any index. It can pick up 4 and it can pick up 5. So that's another myth buster. That's wrong. The order of columns do matter a lot. The order of columns in your select query does not matter, but the order of columns in your index definition does matter. So first name comma email promotion is not the same as email promotion comma first name. Now comes the third thing. Why is the optimizer choosing contact composite 5? Before I answer that to you, is there really a performance difference between 5 and 4? That is something that we all should see. Is there a difference? So what I will do here is, let's remove this option max stop. Okay, let's compare the performance. This first one, let the optimizer choose what it wants, which is it will choose contact composite 5. You have already seen that. And let's force contact composite 4 here. I'm forcing contact composite 4 here. And what are we trying to do? We are trying to see performance difference, if there is any performance difference. So let's execute both of them, jump over to the execution plan. And yes, you can clearly see that there is a performance difference. 41% versus 59%. And the interesting thing is, in both the cases, the optimizer is doing a seek. One is contact composite 5 and the other one is contact composite 4. So what is going on? So friends, before we wind up this session and the last demo, here is the answer. The rule of the optimizer is that it will seek on subsequent columns, right? Let's go and jump over to the query and the index. Let's put them in one window. So it is going to seek on subsequent columns if there is an equality operator in the previous column. The index follows a left-based subset searching mechanism. So it starts from left to right. And if there is an equality operator on the first column, it will seek on the second column. Now, if we apply this logic, this rule of the optimizer for contact composite 5, email promotion is the first column. And in my select statement, I'm using equality operator on email promotion. So it will seek on email promotion, obviously, and it can also seek on first name. But if I apply this logic on contact composite 4, it will seek on first name because L% is seekable, but it's not going to seek on email promotion. Why? Because there is no equality operator on first name. On the first name, we have the like operator. So the rule of the optimizer says that it will seek on subsequent columns starting from left to right if there is an equality operator in the previous column. That's the rule of the optimizer. So friends, in contact composite 4, if this index is being used, then email promotion is termed as a residual predicate. The residual predicate, right? This is the seek predicate, first name, because you're able to seek. But if you have attributes in your index keys on which the optimizer is not able to seek, is called as the residual predicate. Unfortunately, residual predicate is not very clearly highlighted in the execution plan because the execution plan, both of them show up as seek. But if you go to the tooltip, I'm not doing that. But if you go to the tooltip, somewhere in the predicate section on the top, you can figure out that there is a residual predicate. And in case of contact composite 4, email promotion becomes a residual predicate on which the optimizer is not able to seek. And using contact composite 4 becomes slightly more expensive than contact composite 5. Because in contact composite 5, you can seek on email promotion as well as first name. Why? Because email promotion uses equality operator. And when the traversing searching happens from left to right, it encounters equality operator, allowing it to get the exact number of rows and then filter on first name. All of you who chose 4, this one as an option, you were not wrong, because there is a guideline that you put the most selected column as the first column in as the leading key in the index key definition. That's right. But then the caveat here is provided that uses the equality operator. All right, friends, with this, I come to an end of all the 6 demos. You can, of course, friends, go to this link and download all the resources, both for version 1 and version 2. And I will just put this entire thing in the chat window for all of you. All the links are there in the chat window. Friends, do share your feedback on Twitter, _Bansal. I'm there. Hope to connect with some of you. If you like the session, if you like the content, I hope this was something for you to take away and look into your production if there are tuning opportunities. If you go to the resources section on SQL Maestros, you will find all these scripts and feel free to use them. You don't have to give any rights to anybody, no credits required. Just use them and help yourself. Hopefully, you will have something to gain. With this, happy to jump over to questions. We have a few minutes.
Excellent. So indeed, we have 3 questions. We need to find a bit of context for these questions, so maybe you can help me with that. So somebody asked, let me see who it was. It was London DBA. He asked a filtered index where actual cost greater than 50,000 would be better. I don't know exactly to compare to what, but it has to do with the first demo you had.
Yeah. All right. The first demo was okay. First demo was about, just looking at the folder. Okay, it was about sorts. Okay. Well, filtered indexes are. I can just generally answer this because as I would not have more context about the question, but filtered indexes are good solutions. I do not see much use of filtered indexes in production. I fail to figure out why, but they could be good solutions to deploy for helping with tuning, because I see there's huge data now. Data is exploding. Tables are becoming huge, and if we land up creating a lot of non-clustered indexes, we are just duplicating the amount of data. So with filtered indexes for specific querying patterns, can be a good solution. So yes, let's think about that.
Excellent. So we have an anonymous attendee asking whether optimize for is better than force seek. So why use optimize for rather than force seek?
Well, in this example, I used optimize for because I'm just leaving it to the optimizer to decide on the plan. Scanning and seeking were in the demo itself, there were 2 choices between scanning and seeking. So probably that is where the comment is coming from, that let's just ask the optimizer to seek. But then it's just not about scanning and seeking, right? There are different access methods. There are so many different iterators. We are leaving it to the optimizer to decide what it wants to deploy.
Good. And then we have the last question. What do you think about using memory optimized tables instead of temp tables?
So when we talk about memory optimized tables, I'm sure Sasson is probably talking about using in-memory OLTP probably. So in-memory
Yes.
OLTP as a feature is a completely different beast altogether. And if in our example, we let's look at that this way. In SQL Server today, we have 2 parallel engines running. Let me call that out. So we have the traditional database engine that we all use, and like more than 99% of the deployments would use that as an engine. In-memory OLTP is so to say a different engine altogether. If we have to enable in-memory OLTP, we have to think about a lot of different architectural patterns as to how it's going to impact the application, and there are just so many things to take care of. So it's not just kind of easy to enable in-memory OLTP and create memory optimized tables and just kind of start using them, at least not for the example that we have used, because end of the day, any table that we create, we are essentially caching the data in memory. So what are the different advantages that we are going to get? But just because the feature says memory optimized table here would not mean that we are all, of course, agreed that the data for that table will always reside in memory, but that's not the problem we are trying to solve here. The data that we dealt with, user databases versus TempDB, in both the cases, the data was in memory. It was not being read from the disk. Once it gets from the disk into memory, it remains in memory. We, on the other hand, we're trying to solve a different logging problem. And remember, in-memory OLTP design, logging still happens. So in-memory OLTP may not be very relevant to our demo, but other than that, it's not a feature just like to turn the knob on and start using it, like optimize for ad hoc workload. A lot of architectural considerations have to be made. Sorry for the long answer.
Good. We don't have any more questions. Let me see. Nope, I think that's it.
Okay, and I would also invite people to download the new SQL magazine for the community. Many SQL family members have written a lot of good content there. So the link is there in the chat window. Feel free to download the free copy there. Thank you, everyone.
Fantastic. Thank you very much, Amit.
Thank you. Thank you, Ganakula, for helping. And thanks, GroupBy, for having me once again. I can see a few more folks. Hi, Arjanis. Hi, Daniel. Good to see you guys.
Hey, love your
Great presentation.
presentation. Thank you.